Here are solutions to homework set number 11 for ECE 111. This homework set looks at using MATLAB to solve problems that you run into when you take electromagnetics 351, as well as circuits 2. Specifically, we're looking at inductors. When you start adding inductors to an RC circuit, you wind up with second-order differential equations, a thing called the wave equation. So starting out, last week we looked at capacitors. Capacitors are integrators. Inductors are differentiators. So if I have this circuit, and here's the current, to find the voltage, I differentiate. For inductors, the voltage is L di dt, so the voltage will be the derivative of the current times L. If L is 1, it's just the derivative. So starting out, derivative is changing current over time. Between 0 and 1, the current changes by 0 in 1 second, so the slope is 0 over 1, or 0. It's bad 0. 0. Between 1 and 3, the current changes by minus 3 in 2 seconds. So the slope is minus 3 over 2, minus 1.5. Between 3 and 4, the current changes by 0 in 1 second. So the slope is 0 over 1. Between 4 and 6, the current changes by this amount. That's plus 7. Change that in 2 seconds. So the slope is 7 over 2, or 3.5. Between 6 and 7, the current changes by 0. Slope is 0. Between 7 and 8, it changes by minus 7 in 1 second, so it drops down to minus 7. Goes plus 3 in 1 second, jumps up to plus 3, and then winds up back at 0. So here's what the voltage looks like. It's the slope, or derivative of current. So now we have 3 components: resistors, capacitors, and inductors. Resistors are just a gain, V equals IR. Capacitors are integrators. Inductors are differentiators. Going on to problem 2. If we have an RLC circuit, the equations for this wind up being second-order differential equations. Now there's a couple ways to write the dynamics. One approach is as follows. For the capacitor, I know that I1 is C dV dt. So I get I1 is C times V1 dot, and using dot notation to mean derivative. I know that the voltage across the inductor is L di dt, so V0 minus V1 is L Ia dot. I know that over here, V2 minus V1 is IB. That's L di dt. L IB dot. I know that I1 is IA plus IB plus IC. And here's the trick. I can substitute down here if I take the derivative. So let's differentiate this equation. The first derivative becomes second derivative. Here's the first derivative, first derivative, first derivative. Now substitute. When I do that, I wind up with, here's the derivative, the inductors, substitute up here. I wind up with a second-order differential equation. Now when I group the terms, there's a term times V0, times V1, and V2. Group the terms, it winds up looking like this. So this is just like the heat equation, but instead of these terms being the first derivative of voltage, it's now the second derivative. That's the difference between RC circuits and RLC circuits. RLC circuits, I get the second derivative. As opposed to RC circuits, I get the first derivative. In terms of names, the first derivative was the heat equation. second derivative is the wave equation. That's the topic for this week. So this is at node 1. Nodes 2 and 3 will look just the same. Just change the indices. Due to symmetry, everything's the same at each node. Just increase the index. So here's node 2, increase the index by 1. Node 3, increase the index by 1. At node 4, same thing, except that there is no node 5. So this term goes away. And one of these two goes away, because one came from the right. So I just get 1 over LC. So these are the 4 coupled differential equations that describe the circuit. If I plug in numbers, I wind up with this. So that's the first part of problem number 1. Come up with the differential equations that describe that circuit. And again, it looks very similar to last week, but now it's the second derivative. To solve, wait until you take Calc 2, Calc 3, actually I think it's more like Calc 4 when you solve this problem. But using MATLAB, I can solve using numerical methods. So what I do in MATLAB is, given the voltages, given the first derivative, I can find the second derivative. Once I know the second derivative, integrate once to get the first derivative. Once I know the first derivative, integrate again to get the voltage. Plot the voltage, move forward in time 10 milliseconds, and repeat for 3 seconds. So this is what that looks like. So go into MATLAB. Again, kind of a reminder, this is what we did last week. Last week, when you get the first derivative, that's the heat equation. Here's how the heat equation behaves. I've got a forcing function, 10 volts, that charges up all the capacitors. Again, nothing too wild. There's coupled first-order differential equations, heat equation. This week we're looking at coupled second-order differential equations. Make that the second derivative. Now here's how it behaves. Notice it's very, very different. The wave equation occurs over and over again in nature, one of the more important equations. When you have something that's described by the wave equation, it'll behave very differently than something described by the heat equation. This would be things like buildings, bridges, people driving cars, traffic. Those all satisfy the wave equation. You get this kind of response. Going to plot it versus time. Again, very, very different than the heat equation. This is how coupled second-order differential equations behave. And in circuits, you get that using inductors. On to problem 4. The reason this is called the wave equation, it doesn't really show up that well when you have 4 nodes. Repeat if you have 30 nodes. So this is where for loops are nice. What I could do is go back over here, make 30 copies of this. That would work. Another way to do that is use for loops. This is where for loops are kind of useful. I can take the middle 28 nodes, put that in a for loop. I have node 2 as a function of nodes 1, 2, and 3. Node 3 is a function of 2, 3, and 4. Same pattern over and over again. That lets me put this in a for loop. And I'm going to use indices rather than V0, V1, V2. V of 3 means the voltage at 3. The oddity is the first node I can't do because MATLAB hates the index 0. I can't do the last node. The last node's different because there is no node 31. So this equation is slightly different at the last node. So the first node and last node are slightly different. Otherwise, I now have 30 nodes. Well, let's see how that behaves. My forcing function, instead of just being 10, this is going to be kind of a snap that we'll see in a sec. I'm going to go up and down for 2 seconds. Here's my snap. That's up and down for 2 seconds. What that did is that launched a wave. This is why coupled second-order differential equations are called the wave equation. I launch a wave, and the wave travels down the circuit, hits the endpoint, and then there's a thing called a reflection. When I hit the right side, it goes up to double the input, then reflects. I get a plus reflection. Minus in gives me minus out, plus in gives me plus out. On the left-hand side where it's fixed, I get a negative reflection. Negative in gives you positive out. Hit the right side again. Right side is a free endpoint. I get a plus reflection. Plus n gives me a plus reflection. Left-hand side, try that again. Launch a wave. Goes down the line, hits the right-hand side, gives me a plus reflection. The reflection now goes left, hits the left-hand side. The left-hand side is a fixed endpoint. That gives me minus reflection. Plus in gives me minus out. And it's not just RLC circuits. Anything that satisfies the wave equation has this characteristic, be it bridges, traffic, buildings, transmission lines, yeah, you name it. Anything that satisfies the wave equation behaves like this. So this creates a problem. How do I stop reflections? Reflections actually cause trouble. To see how they cause trouble, let's change the forcing function to be 0.5 sine of 3t. So here's my forcing function coming in. Think of that like the ground is shaking for an earthquake, the wind is blowing. I'm giving it a sine wave forcing function. With the reflections, once that sine wave hits the right-hand side, I get a reflection, and I get the waveforms adding, one waveform going one right, its reflection going left. Together, you get these standing waves. You see that on transmission lines, you see that in traffic, you see that in buildings. The standing waves are going to cause trouble. They can cause bridges to collapse, cars to get into traffic jams and basically come to a screeching halt, transmission lines to snap. I would like to get rid of those. So how do I do that? Well, the approach is the problem is the discontinuities. At the right endpoint, it's going up. Let's see, where's it at? So there's my circuit. There's my circuit. The right endpoint is just ending. I don't want to do that. I want to stick a resistor at the end or vary this resistor. If I make it too big or too small to get reflections, what is the Goldilocks number? What is just right? So this last term is 1 over RC. This guy right here. Let's change that at the last node. Let's change this term right here. So if we go into the simulation, and let's just run it for 6 seconds, long enough to see the reflection and have it come back. And this last term right here, what happens if that number is too small? Well, let's try it. If that number is too small, like 0.01, that means 1 over RC is 0.01, R is too large. If that's too small, the right endpoint moves freely, and I get a plus reflection. If I stop it at 6 seconds, I can see the reflection. So that's what happens when it's too small. What happens if it's too big? Let's try 100. When it's 100, you'll notice the right endpoint just barely moves. This is too stiff. When it barely moves, that gives me a minus reflection. Okay, so what is the Goldilocks number? 100 is too big, 0.01 is too small. Let's just do trial and error. Let's try 10. If I launch it with the last term being 10, meaning at the last node, 1 over RC equals 10. At 10, the right endpoint moves. Ooh, that was pretty good. That's almost 0, maybe slightly negative. Let's try 9. Here, just kind of play with it. At what point is the reflection basically 0? Yeah, that's pretty good. Kind of got lucky there. If I go too far, but not quite far enough, at 20, you'll see there's a slight negative reflection. It's better than 100, but still slightly too big. So here it comes down. There's a slight negative reflection. If I go too small, like 5, comes over, it moves freely, and now there's a slight positive reflection. There's the reflection. So it looks like the right number is right about 9. When you take electromagnetics, you'll calculate what that number is. For now, using MATLAB, I can use trial and error and tune it to try to get rid of the reflection. This says that 1 over RC on the last node should be 9. So going back to the standing waves, let's run it for 20 seconds and see what happens if I make the last node 9. Let's do 4 times t. If I do that, I excite it with a sine wave. Oops. I forgot to define B0. Stop that. Try it again. So there's my forcing function. I launch a wave. It goes down, hits the right endpoint. The way I terminated it, there are almost no reflections. So instead of having these reflections come back, causing standing waves, I no longer get the standing waves, all the energy is being absorbed. I no longer have the bridge bouncing up and down. I no longer have traffic jams, freeing up, getting stalled. Buildings swaying during an earthquake, they aren't creating standing waves and collapsing. That's kind of what you're looking for in transmission lines. Using MATLAB, I can simulate it and see the wave equation. I can see what one solution is, how to terminate it to get rid of reflections and get rid of standing waves. That's the wave equation, and using inductors in ECE 111, homework set number 11. And you'll learn more about this when you take 351 electromagnetics. But for now, using MATLAB, I can simulate the wave equation. Homework set number 11.